Okay. So, does anyone want to summarize what we did yesterday? Before I get started with what I have ready. We discussed a couple of problems, right? We discussed, first we started with rock, paper, scissors and tic-tac-toe. And then we discussed two more problems. We discussed like the problem, like the Monty Hall problem, where you have three goats, three doors. One of them has a car, and two of them have goats behind them. And there's also like a game show host, and you pick a door, and then the game show host basically opens one of the other doors, and then the question was, should you switch or should you not switch? Right now, yesterday we kind of saw intuitively why you should switch. Today I'll be going more into detail about like the math behind it, like the probability behind it, and then also like the eight queens problem that I introduced yesterday. We'll be looking at like a more in-depth version of it, and then if we have time, I'll be doing some other things. Okay, so let's get started. This is like again, it's the same problem statement as yesterday. There's three doors. Yeah, one has a car, two has goats. You choose one, and then the question is, should you switch if one of the other doors has been opened? Okay. Uh, there is a probability tree here, but I will just draw my own. Okay. Hmm. So so when I write car one, I mean car is at door one and so on. Okay. Car is at door three. Hmm. Okay. So here, what happens is the host will open door number two, right? Or door number three. Either of them with 50% probability. Right. And uh, either way, if you switch, you lose. Right. So I'm just gonna see the switch case first, and then we'll see the. Yeah. Okay. Either way, I'll draw car two and car three here for now. So once you do car two, he will the game show host will always open door three because you've chosen like if the car is at two because you've chosen the door one, right? Assuming door one, right? So and for car three, the same thing will happen where he'll choose door two, right? And okay, sorry. First, before we start all this, have you guys seen probability trees before, or should I explain what a probability tree is?
We've seen it in Ashwin's class.
So you guys know like for example, like door two being opened, the probability is like 1/6 and so on, right?
The probability of what?
Like the probability of car one
Yes,
being
sir.
chosen and door two will be 1/6. You just
Oh,
multiply
yeah,
these
yeah,
and so
yeah.
on. And then like if you add all these three branches, it'll always add up to one and all of that. Right. Okay. So uh You know what? Let me just do like a nice little thing really quickly. Sorry. Uh, so you have start, and then you have car 1, car at 2, and car at 3. Okay? And then you have here you'll have two cases, door 2 and door 3. Here only door 3 can be opened because the car is behind 2, and here only door 2 can be opened because the car is behind 3, right? And each of these has 1 by 3 probability, and this will have half and half, and then these have 1 probability because that's the only choice the game show host has. You choose one. Okay, so now we'll see the probabilities for if you switch and if you stay. Okay, so if you switch in this case, you'll lose, right?
Yes, sir.
Similarly, in this case, you'll lose,
Yes, sir.
but these two cases you win, right?
Yes, sir.
Huh. And similarly, if you stay instead of switching, then in these two cases you'll win, and in these two cases you'll lose, right?
Yes, sir.
So now, can someone calculate the probabilities and tell me what we get?
The 6, this 2 by 3, 2 by 3 if we switch.
Hmm. Why is it 2 by 3?
Because when we switching wins at car 2, which is 1 by 3 probability, and at
Hmm.
car 3, 1 by 3 probability.
So this has 1 by 3 probability, and this also has 1 by 3 probability.
But in the
But
other ones, when we switch, it's 1 by that both of them together is 1 by 3 probability when we
yeah,
stay.
like each of them separately is 1 by 6 probability. So like this total win condition here is 1 by 3, and this total win condition here is 2 by 3, right?
Yes, sir.
That's okay,
Yes,
right?
sir.
Now let me change the question a little bit. Okay. What if instead of 3 doors, you had let's say you have n doors, okay, and you pick one door. Host opens n minus 2 doors with codes behind them. Switch or stay. What do you do here?
Switch.
And what are the probabilities? Does anyone have any guesses as to what it will be?
Yes,
Yes,
sir.
yes, sir.
What do you think it will be?
Sir, we should switch.
Should switch.
Yeah,
Just which
and we should switch is right. But like, what is the probability we win if we switch?
n minus 1 by
N
n.
minus 1 upon
N
n.
minus one by n. Perfect. Okay. You use the same argument where like originally you had a 1 by n chance of winning, and like this is your remaining n minus 1 by n chance of winning, and like all of that gets concentrated into this one door, so that door has an n minus 1 by n chance of winning, right?
Yes, sir.
Okay. Now I have another slightly different question for you. Okay. Uh, we will go back to having three doors. Okay. Host does not know what's behind each door. Okay. And you pick one. Host opens a different door. And it is a goat.
The host doesn't know but still picks a goat.
Yeah.
Somehow he picks a goat.
Yes. He gets
Okay.
lucky and it is a goat. Okay.
All the times.
Uh, I mean, they're only playing it once. But yeah, the time we play, it happens to be a goat.
Okay.
Should you switch or should you stay? And what are the probabilities this time?
Sir, are there two goats on two doors?
Yeah. One car and two goats.
So which door is having the goat?
So would there be no
We do not
difference if we
know
switch
which.
or stay?
Sorry, what? Could you repeat that?
Sir, wouldn't there be no difference if you switch or stay?
Why?
Since one door is already gone, the other
Okay.
two have 1/3 chances. And since both of them are 1/3, now that one is taken out, both of them have an equal chance of having the card.
Uh, but then what happens to the remaining 1 by 3 probability? Because we know our probabilities need to add up to 1, right?
Then
Like, you remember how last time it was uh, 1 by 3, 1 by 3, 1 by 3, and then like both of these get concentrated into one of the doors. But this time, what happens to the remaining 1 by 3 is my question. Yeah.
sir, sir, I
Hmm.
think it's the same switching only, sir. I think it's the same switching.
Okay.
And the
What
same
would the probabilities
probabilities.
be?
Same probabilities.
Okay. That's one answer. Does
Because
anyone have a
because
different
someone
answer?
else would have kept the goats.
Okay.
If he hadn't
Does
have picked a goat, then like it would have been a 50-50 chance. But since he's picked the goat, it doesn't change. It's like the probabilities are the same.
no, if he hadn't revealed a goat, he would have revealed a car, right? And if he revealed a car, we can't win a car, so it doesn't matter.
Yeah, but the
Uh,
probability is the same.
hmm. So you were saying like because he's revealed a goat, it's the same outcome as last time, so the
Let's say
probabilities
yeah.
are the same.
Yes, sir.
So
Does everyone agree with this, or does anyone else think there's a different answer?
Sir, I agree.
Okay. I want more thoughts. There's supposed to be 30 people, I think.
Sir, can you actually just give the reasoning for why the for the last time like with the same tree, can you reason out why last time it was 2/3 again?
Okay, sure. So I'll just just use this tree this time. Okay. I'll just draw it here because that one's used. So you have your start, and then you'll have 1/3 chance for each door, each car being at each door, right? At 1, 2, and 3. And
Yes.
then here, there's like a half chance that the host opens door 2 and a half chance host opens door 3. But here, the host will always open door um, 3 because the car's behind door 2 and you've chosen door 1.
Sir, which analysis is it, sir? Is it the normal one or the host not knowing?
This is the original question, not the new question. Someone
Oh.
wanted me to repeat it.
Oh, okay, sir.
And similarly, for this, the host has to choose 2, right? And if you see, when you're switching, you lose in these 2 cases, but you win in these 2 cases, right?
Yes, sir.
But like the probabilities are 1/6 and 1/3 for these 2. So in fact, your win probability will be 2/3 and your loss probability is 1/3. Is that okay?
Yes, sir. But once we figured out the goat is a 2, can you repeat how we get 2/3 for the
Once we figured out the goat is at 2, like this case,
uh yes, sir. The goat is at 2 and the car is at 1 or 3. Like once the host opens the door, we find out that the second possibility is not possible.
yes. So then
So
these 2 are not possible, right?
yeah.
Okay, so then you have like a 1/6 chance of the car having been at 1 and like a 1/3 chance of the car having been at 3, right?
Yes, sir.
So your chance is still double, right? Because you
Oh
have a
yeah,
1/3 chance and a 1/6 chance. Yeah. Okay. Let's go back to this question. Yeah. Okay. I'm assuming the rest of you have thought about it. Do you think, does everyone agree that it's still the same question?
yes, sir.
Sir, could you please explain this part of the question again, sir, where another 1/3 is left out?
No, that wasn't part of the question. That's just like someone tried to give a solution, so I was asking that. So they were just saying like originally there's a 1/3 chance for each door, and like because the second door is ruled out, there's now a 1/3 chance for like the remaining 2 doors. But like then I was explaining why like in our previous example, this 1/3 chance also goes to the remaining door. That's why you have to switch. I was just explaining that. Like that's not part of the question.
I was asking about the question in which the host doesn't know about the door.
Yeah, in the part like that's not part of the question. I just drew that because someone was giving a solution. Like that's not part of the question.
Okay, sir. Thank you.
Okay, so does everyone agree that it's still the same question and you should switch? I actually agree with the person who said it doesn't matter if you switch or stay. I just don't agree with their reason for why it doesn't matter if you switch or stay, if that helps. I'm saying it'll still be an equal chance of you winning if you switch or if you stay.
Then how does that happen, sir?
Think
Other
about it.
two
Like,
had a
think
1 by.
about. Yeah, sorry, go ahead.
So since this 1/3 chance is gone, the other two have a 1/3 chance. And since both those 1/3s are equal, it's the
Yes,
same.
but where is this 1/3 chance going?
The
Like
first
last time we said it went here, right? But like this time it's not as obvious.
That isn't the same because we don't know where even the host doesn't know where the goat is. It doesn't matter where
I
the
mean, yeah, that is the main difference. The fact that the host does not know affects our probabilities of winning. But like my question is, why does it affect our probability of winning?
because if we were the host, we wouldn't exactly know where the extra 1/3 would shift
Sir,
to.
if
I mean, I
if you
So,
can tell you where the 1/3 goes, but like I want you guys to think about it. Like the host not knowing is like the only
sir,
difference
but
between
you're
the
not,
previous and this
sir,
one
but you're the
example,
one,
right?
sir, for example, you're the one who set it up and we are the host. Like that I was saying.
No, 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 no. Like forget the whole set it up thing. Even if it was like three random things and like we're doing this, it still works. Like it doesn't matter who knows who doesn't know. As long as the host doesn't know and the host is opening the doors, it doesn't matter. Okay.
so
Uh
if we
yeah,
draw the tree diagram again,
yeah. That's what I want you to do. I want you guys to draw the tree diagram and see where like this 1/3 probability is going.
yeah. So last
Hmm.
time we cancelled out two of them, but this
What do you
time,
mean we cancelled out two of them?
so we can now once we found out that the goat is a two,
Hmm.
we know that the host knows the goat is a two, and that means the host won't open. And if the like in the tree we cancelled out the probability where the goat is at the like the threes are the host opens the threes.
Yes.
So but over here we can't do that because given that the host itself doesn't know that there's a car or there's anything behind the tree.
Uh, okay, how about this? Like that's so the tree itself will be different, right? Because like we're
Yeah.
getting different probabilities. So how about you guys try to like draw the new tree and then we'll see like what's happening and why there's a change happening between them.
Then in the new tree, should we add the situations where the host opens the car door by accident?
Should
Should
we?
we or add the situations
Yeah,
where
yeah. I mean, no, I'm asking you, should we? Because like here it says it's a goat, but like does that mean we add it to the tree or we don't add it to the tree? Does anyone
the
else
car?
want to answer this question?
So the car, adding the car, the host picking the car.
Okay. Yeah, like I understand your question, but like I don't want to answer it. Can someone else answer it? Because like I don't want to give it away.
So what was the question?
So when you're drawing the probability tree, do you have to add the scenario where the host picks the car by mistake? Even though the question says the host opens the door and gets a goat.
But I think we actually do need to add that situation.
Yes.
So we can have the switch and the staircase wrong as
Hmm.
0. So I think we do need
Exactly.
to
That's
add
the
it.
main difference between the previous case and this case. So I'm gonna get rid of this.
Yes, sir. This half a 50%, 50%.
Yeah. So this time what happens is car at 1, and then host opens 1, 2 or 3.
Sir, actually
Back
the
to
the thing is, if we switch, it's 33% probability. If we stay, it's 33% probability. And if the car host picks the car, that is a 33% probability.
exactly. So basically, we've picked one. Okay, choose door 1. Okay, and all of these have 1/3. Now that we've picked one, the host has to choose between 2 and 3, right? And that's like a half probability. Similarly, there's a half probability here and here. Because the host has no idea which has what. So like the host will just randomly choose between um, door 2 and door 3, right? So now in these two cases, game ends. In these two cases, game ends. Because host reveals car, right? Is it okay so far?
Yes, sir.
So now you're left with two more sets, obviously. One is the switch and one is the stay. Switch loses these two and wins in these two. Stay wins in these two and loses in these two, right? But here's the thing. Now all of these have probability 1/6. I know this is invisible. One second. All of these now have probability 1/6. Right. Is that okay?
Yes, sir.
Yes, sir.
So now can you guys see why we're getting it doesn't matter?
Yes, sir.
Like whoever said like the 1/3 originally is right, but what actually happens is that both of these 1/3s get split into 1/6s, and the 1/6s have win conditions, and like the remaining 1/3s where the game ends because the host chose the car. Okay.
Yes, sir.
Hmm. So that's why it doesn't matter if you switch or you stay in this scenario. Okay. Uh, yeah. Okay. I gave you one more question yesterday. It was yeah. I left you guys with the 8 queens problem, right?
Yes, sir.
How many solutions were you guys able to come up with?
Sir,
Sir,
I would
man,
find
sir,
one, but then I like flipped it and I got more
Hmm.
solutions. So
sir, I may found one long time ago, but I forgot what was the solution. But then I forgot
Okay.
to do today.
Mm-hmm. Anyone else?
sir, actually I think the one you're having is um I think I also no, I have a different one.
Hmm.
So
But yeah, what? Yeah, go ahead.
I tried by placing each queen per row and per column.
Okay.
Means one in one column and one row.
Hmm.
From there I got 36%. My
How many?
solutions.
Sorry. Your voice is breaking. I can't hear anything.
This camera's frozen.
Is it like my network issue, or like can you hear me, or is it like this thing?
Sir, his
I think it's his.
camera's frozen. His camera
Okay.
looks frozen.
Okay. So you just continue till he comes back then. Okay. So someone said they found one solution and then they did like flips and rotations till they got more solutions, right?
Yes, sir.
How
Sir,
many
but
solutions did you get in total from your one original solution?
I'm not sure. I think I got 4, but I have to check whether they're all different or not.
Okay, sure. Someone else had something to say?
sir, like we can move the queens row by row and check if there's more solutions that way. Like moving the queens like pawns one step forward and then putting the eighth row queen back and then keep on doing it until we find solutions.
Hmm.
I
Like you're
found
saying just move this here and then move this here
No,
or
sir.
something
Like
like that.
the first 7 queens we move front and the eighth queen we move
Okay.
back. So
Hmm.
I learned this. I learned this thing from one of my someone. They told you can do this
Okay.
in this to
So let me
see
just
the
like
solution.
explain what he's saying. So like this probably won't be a solution, but like just for like a demonstration.
You can do it until you find a solution.
Yeah.
um,
So what he's saying is you move all of the queens forward one. Right. Yeah. I know it's not a solution, but like just to make sure there's one in every this thing. Okay. So you move everything forward one, and then whatever is on the eighth rank, you move that to the first rank. That's what you're saying, right?
Yes, sir. Like we can repeatedly doing that until and we see if we have a solution.
Hmm. So something like this is what he's saying. You know what? I'll do it with the solution we have on the board.
Sir, I got 4 solutions by rotating the board.
Nice.
You can mirror them also, you'll probably get more.
And
sir,
flip it and rotate.
I got 12 different solutions from just one question.
One from one position.
I'm sorry, sir, not 12, sir. I got 8 different solutions
Eight.
from.
So yeah, from like most of the solutions, you'll get eight different positions. You can rotate it like three times to get more, and then you can flip it, and then you can rotate the flip thing to get four more.
And I also
But
did his method, sir. I also used his method, sir. This method,
yeah,
moving one piece.
we'll just look at that. So something like this. Uh, but like this clashes, so we push it one more time, is what you're saying.
So like that until we get more
But then,
solutions.
like, no matter how many times you push, these two will always be clashing with each other, right?
No, sir. If we push it 5 times,
Or
we
still
push
like
it
this
five.
loops back here.
Yeah, it will move back there.
Okay, I'll push it like three more times then. Okay.
Sir, one more thing.
Yeah,
Sir, I found a website where you can do the 8 queen problems online, sir. Also.
nice.
So
Well,
can I share that website so that it will be useful for everyone?
Sir,
how about
otherwise,
we do that at the end of the class?
sir,
Okay, sir.
otherwise we can
After,
also do the same thing horizontally or
yeah. One second. You said this, so like let's see this, and then yeah, and but
sir,
now
it
you
still
get this
doesn't work.
clashing. Yeah.
Oh, sir, this type of thing doesn't work.
So like there's not always a guarantee that like such a solution exists. Because now even if you do one to the left, right? Uh, this. See now you get a solution. If I'm not wrong. Yeah, now you get a solution. But
Have
like you have to
you
check all the vertical and horizontal pushes. And in fact, this is a new solution that's different from the original solution we started from because that had a corner piece and this does not. So like this is like a brand new solution that you'll get no matter like it's not symmetric to the original one, right?
Yes, sir.
So yeah, like this is a good way of approaching the problem and like trying to find more, but like you're not guaranteed to find one every step is what I'm trying to say. Or even like no matter how much you push forward, like there's no guarantee you'll always find another solution. But yeah, like that's a
Then,
nice
if we
approach.
push forward once, would there be a solution? Just asking.
Sure. Yeah, we can
Yeah.
check. Yeah, this is also a solution.
Yeah.
But I think this is symmetric to like our original solution if you just rotate it twice.
Oh,
Like this solution where you have this, and this. Yeah, it's just like our old solution except it's been rotated twice, right?
yes, sir.
Yeah. Um. Yeah. So does anyone else have any other ways of getting new solutions from solutions we already have?
Do mirrors and rotations count or no?
We'll have two different counts, one for unique solutions and one including mirror images and rotations.
Sir,
So, so like
there's one
for,
method, sir. Reflection. The reflection method.
yeah. So yeah, so like given anything, in general we can get up to 8 solutions from it, right?
Yes, sir.
Hmm.
So the
Uh
reflection method says that you reflect it completely opposite, to mirror it.
yes. That's how we get 8, right? Because if you
Yes.
rotate this board, you'll get 4 solutions.
Hmm.
And then after you take the mirror image, you rotate it and you get the 4 more solutions.
Yes, sir.
Yeah, perfect. But now here's a question. How many like fundamental solutions are there? How many base solutions are there if we ignore all symmetries and we don't count like into 8 or whatever?
Sir, I checked that also, sir. There is 12 different unique solutions.
Yes. What are the 12 solutions though?
I think I stored it somewhere, sir. Wait, I'll just read it out if I have it, sir.
If you've seen it online, try not to like give it out. Let the others think for a bit, and then we'll discuss it.
Yes, sir. After I did the solutions on myself, sir, but
Hmm.
I just saw how many maximum possible solutions are there uniquely and
Hmm.
mirroringly.
Hmm.
I will read it out when you want me to, sir.
Yeah, sure. So, like the rest of you, just think about how many unique fundamental solutions you've gotten so far, and we'll like let's try to get the 12 number that he's saying, and then we'll see if that's the maximum or like and like how to get the overall total number of solutions including symmetries.
Sir, I found another easy method to find the solutions for the 8-pin problem, sir.
Okay.
We, as the queen can't move in the L shape, which the knight can, we can always track that method and place the queens there and try to do it.
Yes, sir. I had a similar solution, but so I got one solution like that, where the first one is in the bottom left corner.
This,
Then
right?
you play a horse move for the second one. Like
Hmm.
vertically, the one above it will be a horse move. Oh yeah, that is also fine. Yeah, that also makes sense.
Sir, but
And
this
you
is
can
not a
flip this.
So
solution.
this
Sir.
is not a solution.
The one on the board is.
Yeah, because of the queen here, right?
Yeah.
Yes, sir.
Sir,
So how can we adjust this to make it a solution?
Sir, when I first saw this problem, I was thinking of horse moves completely.
Hmm.
And then I did, when I saw it in second standard.
So you can move the queen on h8 to h3. No. No, no,
That's right.
no, sorry.
Sir, I don't think you can keep any of the queens in E8, F8, G8 or H8 because all the 4 queens in the queen side of the
Right.
board is controlling it.
Yep.
When
That's
you
the
do-
problem with starting like this. This gets covered, so you can't actually do it. So like he pointed out, if you start like this, there's actually no solution.
Sir, we can move the queen at e8 to e3, sir. Or no, we can't. We
So
can't.
you watch.
So you can move the queen on a1 to a the a8, yeah, and that queen down.
Yeah, but then they're on this diagonal now, right?
Oh yeah.
Then, sir, can we like keep camel moves? Yeah, like they're going 3 and then 1. Like a knight, but 3 steps and 1. Like that, can we keep?
You mean something like this?
Yeah, yes, sir.
Again, the problem is on the last queen you end up here, right?
Sir, but there is no queen. Sir, we can like move the queen. We can adjust it by moving the queen on E6 to somewhere.
Yeah, but where do I move? Because I need something on this row, right?
Yes.
And the
sir.
thing is, these all are blocked out,
Oh,
right? And like this
yes.
blocks these two.
Sir, I have an idea.
Hmm.
Oh no.
Sir, what if we keep 3 of the the first 3 queens correct, and then we keep 3 of the queens on E2, F5, and G8, and then we try to find out a place for 2 of the queens. The other 2 queens will find.
That is more doable. Okay.
I have a
So here's the thing. Here's what happens, right?
Oh yeah, we cannot keep.
I'm leaving these two queens here for now.
Oh yeah, we
This
cannot
blocks
keep.
off these. This blocks off these. And then these
Oh
block
yeah,
these. So this
the
entire row is blocked.
Sir, I've seen this actually is a programming problem.
Yeah, it like originally it's a programming problem, but like
Sir,
it has some nice properties of symmetry, which is why I was like, let's
Sir,
discuss
it's not
it
as
further.
a chess problem.
So I have a solution.
Okay.
So you leave A1 where it is. Then in the B row, you put it at B6.
Okay.
Then you do C8.
Okay.
Then you do 1 second. This is D2. Then you do E4. Yeah, E4.
Yeah.
You do F7. Then
They
you
can
do
say it doesn't work.
E5. And then you do H3.
Sir, it's not a solution.
These two are attacking each other, right?
Sir, I think
And these two are also attacking each other.
Sir, I think the knight move approach, we can keep the queen on a6, b8, then c2, and then we can keep queens on
1 second.
a6, b8, and c2,
sir,
Okay.
I have a
and
solution.
then we can. Sir, do you
1
think
second.
that
Let
up?
him finish and then I'll listen to your solution.
Sir,
Yeah,
can you
continue.
remove the rest of the queen? Sir, then we can keep d5, maybe d5.
Hmm.
Sorry, d4,
Okay.
and then queen on e1, then f 3,
Hmm.
g7. G thing doesn't work. So we cannot keep on it. Sir, instead of that,
Okay, how about
sir,
you try
sir,
it on paper or
sir,
like on
one
a board
second,
and
sir.
then.
Can you keep it on f7 and queen on h3? Does that work? Does that work?
Yeah, this is a solution.
Uh,
Okay, and this is also another unique solution that we haven't seen before, right?
Sir, have you seen before there is a queen on b something?
I mean, we did see one with like a2. I'm not
Seven.
sure if it's the same. No, this isn't a mirror, like a rotation of that. This is a unique new solution. Okay, so here's the thing. Like he said, there are 12 unique solutions. Let me show you the all 12 unique solutions first, and then we'll think about how many symmetries each of them has. Okay? So these are the 12 unique solutions. Uh, so if you want to do the knight thing, like that is the first solution, you have to start with the queen on a2 so that like we block out a8 with one of our own squares. Okay? Because otherwise, you remember how I said the eighth row gets blocked off. So we have to put one of the four in the row on the eighth square in like such a knight pattern. Okay? That's how you do that. And yeah, just go through these. I want you to try to count how many symmetries each of them will have.
Sir, mine was the sixth solution.
Uh,
Mine was the sixth
yes, yours was
solution,
the sixth solution.
rotated 180 degrees.
And flipped. Yours was also flipped, right? Like yours was just flipped along this axis. Like this goes here and this goes here. Right?
Yeah, yes, sir.
Hmm.
Sir, I found another solution, sir, and now I can turn, sir. Now I have 16 solutions, sir.
Nice. Which of these 12 solutions did you find?
1 second, sir. Let me just
Yeah.
check it. Um,
Sir, I had
Check the
found the
rotation
11th
and
one.
the reflection.
Nice.
A2, C, no, B2, C4. Even has B2, 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 B2.
Okay. So, does anyone want to like try to guess how many total solutions there are?
Sir, I think I already told that also, if I'm correct. I'm sorry.
Yeah, yeah. Do you want to explain why it's 92?
I'm not exactly sure why it's 92, sir, but
So, what we noticed is that each of them have eight. Sorry, one second. Each of them have eight symmetries, right? Like four rotations and then four flips.
sir, your screen is not visible.
Oh,
Yes, sir, it is.
can you see it now? So we have eight symmetries for each of the solutions, right? Where you have four rotations and then like you can like flip it four times. Is that okay?
Yes, sir.
Yes, sir.
So now there's 12 solutions total, which means 12 times 8, there's supposed to be 96 solutions, but I'm saying there's only 92. Can someone tell me why that's the case?
Because some of them are mirror to 4 of the solutions are already found
The
mirror.
solution 12, when we rotate 180 degrees,
Rotate the
it
solution.
is,
You can
sir,
get the 12 and make it 92.
so
One
that
second.
in, sir,
Solution
in
12, yeah?
solution 12, when you rotate 180 degrees, it's the same thing.
Perfect.
And when we flip it and rotate 180 degrees, then
It'll be the same thing again.
and
Yeah,
then if we flip it along the horizontal axis and rotate it by 180 degrees, it's the same thing.
perfect. Yeah, exactly.
And then wait, where else is it there? Wait,
You want to try guessing why solution 12 has that special property?
yes, sir, I'm trying to understand.
Sir, can
Because
I tell that?
Okay.
Sir, because solution 12 is, what should I say? Something like a parallelogram shape, if you can see it. Or it has two big L's.
I
Two
mean,
big
yeah,
L's.
I see what you mean,
there an
but
L and
like,
the rotated L.
uh,
There's an L and a rotated L.
And there are two L's. One L and one
hmm.
inverted L.
I mean, yeah, like, yeah. So basically, what we want to say is that it has a rotational symmetry of 180 degrees, right?
Yes,
Yes, sir.
sir.
So basically, when we rotate it, what ends up happening is this thing. But there's also like another interesting thing where it's the only one with no queens on its diagonals,
Oh, okay.
which is why it has rotational symmetry. Because if there was a queen here, right, then each of
Yes.
these will be unique, right?
Yes.
Yes, sir.
And that's true for any of the diagonal points.
Yes, sir.
That's the
Yes,
other
sir.
important thing about solution 12, which is why it has that rotational symmetry property that's helping us. So
So,
all 11 of these will have 8 solutions. That's 88 solutions. And then the 12th one will only have 4 solutions. So that's 88 plus 4, 92. Okay?
Oh, okay.
Hmm.
oh,
One interesting thing is, at least from like a mathematics perspective, we don't really have a like strict formula of any kind to generate all the solutions of one of these puzzles. Like we know what all the solutions are for some of them, but we can't exactly generate them. Like for example, yeah. So if my board is size 1, obviously I just put the queen in, there's one solution, right? And like 2 and 3, there are no solutions. Sorry. But from like board 4 onwards, like boards of 4 size, so like, sorry. Uh, queen I believe it's queen here. Uh,
Oh, yes, sir.
I believe
Can
this is
you,
the only solution. And this, but then you can also like do them in these boxes instead.
yes.
Those are your two solutions for boards of size 4. And then board of size 5, you'll have like two things, but then like with symmetry they become 10 and so on. But one thing you'll notice is that like as the number get bigger, it gets like really big really fast. Like we only had like 92 for board 8, but then by board 12 you have 14,000 solutions. Here's the thing, right? We only know how many solutions there are up to boards of size 21. We don't know how many solutions there are beyond that. And like how we calculate this is we go through every possible arrangement and then we rule out all the possibilities that violate our conditions.
Sir, but we can do this using programming, right? We can find more.
That is how we've done it up to board 21.
Sir, actually, that has been found till board 26, sir.
26? Okay, last time I checked it was 21. Sorry.
Sir, do you
Uh,
want me to read out the solutions?
yeah, how many solutions are there for 26?
Yes, unique solutions for board 22 is the 336,376,244,042. For
Hmm.
board 23, it's 3,29,242,658,210. For board
Hmm.
24, it's 28 trillion for
Hmm.
439,272,956,934.
Hmm.
For 25 into 25, it's 275 trillion 986 billion 683,743,434. For
Yeah.
26 into 26, it is 2 quadrillion
Hmm.
789,789,466,510,280.
So, yeah, and sorry, once, yeah, and it's been calculated up to 27 cross 27. But if you notice, right, like beyond this, like even if you like, yes, there exist programs that calculate it, but like even those programs will take way too long to run, right?
Yes, sir, it will take over
Like, yeah,
25 days
huh,
at
and
the
like
minimum.
exactly. So, what happens is this is already like what millions, billions, trillions, like yeah, this is already 29 quintillion and yeah, quadrillion, and like after that, it's just not basically viable for people to calculate the number. And also, like what we're trying to do is we're like trying to mathematically find a formula that generalizes and like captures the symmetries of the board instead of just like calculating it using programming, because even like programming has its limits. Just because something can be computed using a computer doesn't mean we have like the necessary power required to compute it.
So, because it's an n into n to the power n,
Yeah,
of n to the power n algorithm.
yes, the algorithm is open to the power n. Yeah. And like even if you don't see that, like just the number of squares on the board alone increases like at n square rate, right? Even that's exponential. So like not exponential polynomial, but like it's increasing exponentially in the mathematical term, if not the computer science term. So what happens is you have n square squares, and then like when you're seeing like all possible arrangements of the queens, that becomes something like n square choose n, right? And then this will have like an n square factorial by n square minus n
Yes.
factorial and all of that. So you have like n square factorial on the top. So like that gives you an idea of how big this gets like really fast. Because like even for like board 20 or whatever, that's a 400 factorial at the top, which is why you have that many possible cases you need to check and then like calculate all the solutions, right?
Mhm.
So in fact, like actually, if you check, it'll be like uh, n to the power. It'll be even more than n to the power n for whoever said it's n to the power n. But yeah,
Sir, it's something like n tetrated to n.
yeah, something like that. I don't think it's that big, but yeah. Uh, okay. So that's pretty much what I wanted to cover. I have like one fun little exercise for you guys that I want to leave you with. I'll just state the exercise. Does anyone have any doubts so far?
Uh, Sir, not a doubt, sir, but remember,
Yeah.
you asked me to share the website link I said at the end of the session.
Uh,
Can I share it now?
yeah, you can just send it in the chat.
Okay, sir.
Hmm. Yeah. Okay. So I have one final question to leave you guys with. There's 6 people in a room. Okay. They're A, B, C, D, E, F. Any 2 people are either friends or strangers. So that there exist 3 mutual strangers or 3 mutual friends at least. I should have probably typed this, but yeah. Yeah.
Sir, I have a question. Isn't this something like, what should I say? I think the answer for this is something like 6 choose 2.
What is six choose two?
1 second, sir. 6 choose 2
So can't we use like pigeonhole principle or something like that for it? Because
That's right. You will have to use pigeonhole principle.
yeah, because it's like we have 2 boxes. One box contains friends and one box contains strangers, and we have to allocate the 6 people into that.
Yep.
So then, like, if if this is not true, assume that this is not true, then there will be 2 or less mutual strangers and 2 or less mutual friends. So that will mean 4 or less people. But there are 6 people, so it doesn't work out.
No. So what? We can't generalize that fast because it could be that like A and B are friends and B and C are friends, but then A and C are strangers to each other, right?
Yes, sir.
So we can't just put it like this is a box of friends, this is a box of strangers. Like
Oh,
the
okay.
relation between each person matters.
Sir,
Yeah.
can we draw like a hexagon and then use 2 colors?
Connected lines.
We connect
Yes,
lines
so that's the idea. Yeah.
and then we have to find uh like we connect the friends with one color and strangers with another color like that.
Yep.
So the
That's
graph
the
would
idea.
have 15 edges because then
Yeah.
62 is 15.
Yes, sir. So is the answer 15 for this question, sir?
I mean, I'm
No,
asking
you're
you to
supposed to
show
prove.
something, right?
Oh, proof question. Sorry, sir.
Yeah.
A and F. Sir, I have a question. Are for example A, B, B, C, C, D, D, E, F, and F, A, F are always friends, or is it our choice?
That
It's
would
our choice.
Okay, thank you, sir.
Okay. It's not letting colors. I will just use this, but yeah. So let me just give an explanation first. Yeah. So A will either have three friends or three strangers, at least, right?
Yes, sir.
Yes, sir.
Okay, let's first start with the case where A has five friends. Okay.
Hmm.
So everyone is A's friend.
Okay.
Then what happens is, as soon as anyone else is friends with each other, we have like a
in a
set of
triangle.
three mutual friends, right?
Yes, sir.
So we can't have anyone be friends with each other. But then what happens is that we have a group of three of them who are all strangers to each other, then, right? Because we know none of them are friends to each other. One
Hmm.
second. I'll try to draw this because visualize. Give me a second.
Sir, by that we mean like by three mutual friends we mean each person in the three people is a friend of each other, right?
Yes.
Okay, sir.
Yeah. So what we have is we
Sir,
have
just hello, Hurudaya sir.
yeah 5 minutes. I think.
Just a gentle reminder, we are left with 4 minutes.
Yeah.
Yeah, try to wind up.
So we have A, B, C, D, E, F, right? And what I'm gonna do is I'm gonna mark if they're friends, I'm gonna mark it with green. Okay. So we have all of these as green. So what we have is if any of B, C, D, E, or F are friends with each other, then we already have a set of three mutual friends. That's okay, right? Which means all of them have to be strangers to each other.
But then that makes mutual.
But then, like, then we have three mutual strangers, right?
Yes. So we
Yes.
basically have to try to
Hmm.
disprove it, and then we end
Yeah.
up proving it in the end after having many cases.
Exactly. So I'll just quickly go through all the
Proved by
cases.
contradiction.
Yeah, I'll just quickly go through all the cases because we're running out of time, and you can just like go through the recording once they send it to you. Okay. So the next case is like when A has four friends. It doesn't matter which four I choose.
Yes, sir.
We
It's
do something
proved.
similar again, where
Yes, sir.
like
It's correct. Yes, sir. That exists.
yeah,
I just
because
checked all
B,
the
C,
cases.
and D. Yeah, because B, C, and D cannot be friends with each other. Because if any of them are friends with each other, we have a triangle with A.
Sir, if we
And
have
because they're
three,
not,
sir, if we have
hmm,
three itself, then that will
yeah.
happen.
So let me just do it with three, basically.
And then two
Just
also something.
yes. So if A is friends with B, C, and D, for example, right? Then what happens is B, C, and D cannot be friends with each other because then you have a triangle with A, and they're a set of mutual friends. But then that means B, C, and D are mutual strangers to each other, right?
Yes.
Yeah.
So
And for the other cases where like two and one, as you were saying, that's just like it's the same thing where instead of three mutual friends, you have three mutual strangers.
So
But
we're
then like
trying
the
now.
problem we've defined is symmetric, right?
yeah.
Yeah. Yeah, okay. That is pretty much what I wanted to cover. Um Yeah, he's also sent the link for the 8 queens problem in the this thing. Does anyone have any doubts?
No, sir.
Sir,
Hmm.
is there a more like non-casework pigeonhole principle proof?
You can just, instead of cases, you can just directly do the one where they have 3 friends or like 3 strangers. Like the final thing I drew, and then because of that argument, you can say that like anytime they have more than 3, it will become a subset of this case. And anytime they have less than 3, it's the 3 strangers thing, and again, it will be the same case. So all you have to do is one case in the end.
Oh yeah.
Yeah. Any other questions?
No, sir.
Okay. Thank you then.
Hello, Hurudaya sir.
Yeah.
Yeah. Uh, a flawless lecture from you. Just here's a vote of thanks for you.
Okay.
Like on behalf of the all participants and the organizing team, I would like to express my sincere gratitude towards you and for delivering such an insightful and engaging session for the N Queen's problem. Today's lecture was truly interesting and enjoyable for all students, and students really enjoy to discuss with you and to the real life problem solving and strategic thinking. The examples were so good to think, and we had a wonderful discussion with you during the session, and everyone truly enjoyed interaction and sharing ideas about different possible solutions. Thank you so much, sir, for your valuable time, patience, and enthusiasm to teach students. And thank you, everyone.
Thank you.
Thank
Thank
you,
you.
sir.
Thank you,
Thank
sir.
you.
Bye, sir.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.